Okay, there, grade 12s. Today we're going to take a look at one more style of balancing, and this one's probably the most flexible, and it's balancing an acid and base solution. A lot of redox chemistry requires the solution to be somewhat acidic or somewhat basic, and we're going to start taking a look at how we can use that to help us balance a reaction. So you're going to find information about this. It's quite often called balancing by half-reaction method, and we've got sections on it in our textbook. And just by the title, the idea of half reactions, what we're going to do is we're going to separate the reduction half of the reaction from the oxidation half of the reaction. And then once we have them separated, we'll balance each half of the reaction separately, and finally we will put them back together to make a whole reaction again. In your notes, you have this set of steps for balancing if the solution is acidic. It's pretty much the same if it's basic. We just have an extra step at the end. We'll get to that in a moment. But whenever we are going to balance a redox reaction in acid or base solution, we start by dividing the reaction into the oxidation and the reduction half reactions. Then to balance each of those half reactions, we start by balancing all of the atoms except for the oxygen and the hydrogen. In other words, we're going to balance our redox species. And we do that by using a coefficient. Then we're going to balance oxygens by adding as many waters as we need to, because of course this is its solution, so we're going to have water in abundance. We can balance and offset in hydrogens by adding protons, hydrogen plus 1 ions. And again, if it's an acidic solution, we will have these in abundance. And then finally, we're going to balance the charge difference that we created by adding electrons. We'll then find a common factor to cancel our electrons and put everything back together. So we're going to do redox species, oxygen, hydrogen, electrons, and then re-put it back together. Okay, let's take a look at an example of what's going to happen with this. Again, I'm going to put the steps up to the side here in red. We're going to do the redox species first, then oxygens using water, hydrogens using protons, and charge using electrons. I'm keeping this here just as a little reminder of the steps that we're going to follow. So you'll notice that I've got a little chart prepared. I like working vertically. I find I make less mistakes that way. And we have a reaction, and from this reaction you can't tell if the solution's acidic or if it's basic, but I'm going to tell you right now we're going to balance this one in acid. So before we can do that, I have to decide who's oxidized and who's reduced. So we're going to go and assign all of the oxidation numbers. So iodine as an ion has an oxidation number equal to its charge -1. It'll be the same for the chlorine. Iodine in its molecular form is defined as having an oxidation number of 0. Now for the chloride ion, each oxygen is -2. 3 of them accounts for a charge of -6. So the chlorine then has to have an oxidation number of +5 in order to maintain the +1 charge that we have, the +1 charge that we have on the oxidation number for chlorine, on the chloride ion. Now that we've assigned the oxidation numbers, we can see where the changes were. We can see iodine's charge went from -1 up to an oxidation number of 0. That's an oxidation because the oxidation number went up. So I'm going to actually write that half of the reaction underneath the word oxidation. I minus turned into I2. Really important here that you don't drop any charges. It's one of the most common mistakes kids make. Where's the other change that happened? Well, the chlorine here went from a +5 oxidation number down to a -1. That's a reduction. So we have ClO3 ion turning into Cl ion. Now, when I draw these connecting lines, you put everything that is there down to the bottom. The ClO3 turned into the Cl. I know we have extra ions available, and that's okay. We just want to make sure that we have everything that is molecularly bonded together. If this was an ionic compound, I could separate the ions, but we really don't need to for what we're doing right now. So right now, the entire species that is involved in the oxidation and in the reduction. Okay, now that we have separated the reduction from the oxidation, let's balance each half of these reactions separately. Start by looking at the redox species. Under the reduction, it was the chlorine, and I see that I've got one chlorine before and one chlorine after. So far, we're good on that side. As far as the oxidation half reaction, there's one iodine on the reactant side and two on the product side. We can correct this by putting a coefficient of 2. So we've now balanced the redox species. Step 2, balance oxygens by adding waters as needed. Now there's no oxygens in the oxidation half reaction, so we don't have to worry about it for there. But for the reduction, we can see that there are 3 oxygens as reactants and none on the product side. So to correct that, I'm going to add 3 water molecules. Each water molecule is bringing 1 oxygen with it, so now I've got 3 O's before and 3 O's after. This step is done. Step 3. Let's balance the hydrogens by using protons. Remember, I told you this is going to be an acid. So there's going to be lots of free protons available. Again, this time in this particular reaction, there are no hydrogens to balance on the oxidation half. Quite often there are, but there aren't in this case. On the reduction half, however, I can see that we have 3 hydrogens times 2 is a total of 6 on the product side. And so I need to get 6 on this side, so we're going to add 6 protons. Now remember, protons come with a charge of +1. That's really important. Don't drop any charges. Now my hydrogens are balanced. So both of these half reactions are completely balanced in terms of the number of each type of atom available. Where they're not balanced is the charge. In any reaction, the charge must also balance. So in order to balance the charge, we have to figure out what the total charge is before on the reactant side and on the product side. I'm going to switch to green to show you what the total charge is at the moment. From the chloride ion, there's one of them with a charge of -1. I've got -1 in charge, and from the 6 protons, I've got +6 in charge. On the reactant side so far, I'm at a total charge of +5. Going to the product side, we have 1 chlorine -1 ion, so there's 1 minus in charge, and 3 waters, and the waters don't have any charge. So when I add these 2 up, we have a total of 1 minus on the product side. So clearly, I don't have the same charge as reactants and products. The reactant side is much higher. And since I can only add electrons, which are negative, and bring the charge down, you always add your electrons to the side that has the higher charge. So to bring a charge of +5 down to a charge of -1, I'm going to need to add 6 electrons. +5 and -6 is -1. The reduction half is now balanced. Let's take a look at what's going on in the oxidation half reaction. Again, I'm going to do the charges in green. I don't want to mix these up with the reaction itself. I just want to show you my thinking. There's 2 minus 1, so there's a total of 2 minuses here, and an I2 has no charge on it, so there's a total of 0 charge there. In this case, the 0 is much higher in charge than the -2, and I need to make them equal. So to bring that down, I'm going to need to add 2 electrons, because 0 and -2 is -2 on the product side. I now have -2 on the reactant side. Now the total charge before and after is equal. So at this point, what I want to do is I want to get rid of these little green numbers, because I was just trying to show you my thought process for figuring out the total charge before and after. Okay, now have a completely balanced reduction half-reaction and a completely balanced oxidation half-reaction. I need to put these back together. But before I do that, I want to make sure that my electrons are going to be able to cancel each other. Now, there's a couple of things I want you to check at this point. We know reduction is the gain of electrons, so we really should be seeing electrons coming in as a reactant on the reduction half-reaction. I also know that oxidation is a loss of electrons, so I should really see my electrons being on the product side being shown as coming off on the oxidation half-reaction. If we don't have electrons on opposite sides of the arrow between my two half-reactions, you've done something wrong. You may as well stop here and find it. There's no point in moving on. But 6 electrons and 2 electrons are not going to cancel. I can see, though, that a common factor for them would be 6. So I'm going to multiply this whole side of the reaction by 3, and that's going to make 6 electrons to cancel. So let's take and rewrite these two half-reactions horizontally, because I find that we make less mistakes that way. So writing my reactions horizontally, I'm going to start with the reduction. It really doesn't matter. I have a ClO3 minus ion and 6 of the protons and 6 of the electrons on the reactant side. On the product side of the reaction, I've got a Cl minus and I've got 3 water molecules. From the oxidation half-reaction, remembering to multiply by 3. On the reactant side, I've got 3 groups of 2. I have 6 I minuses. I like to line up my little reaction arrows because, again, it makes it easier to cancel, and you'll find you make less mistakes that way. On the product side, again, remembering to multiply by 3. I'm going to have 3 I2s, and 3 times 2, 6 electrons. Okay, we now need to add these back together, and we're going to do some canceling. The first thing that you should make sure cancels entirely is your electrons. 6 electrons in cancels 6 electrons out. If they don't cancel completely, you may as well stop, go back and find your mistake, because somewhere something's wrong. Always check to see if anything else cancels. Very often we're going to have protons or water molecules canceling. In this case, we do not. So at this point, we have nothing else to cancel. We cancel from the reactant side to the product side. So let's put this all back together. What is left now, I have ClO3 minus and 6 protons and 6 iodine ions, and that's everything on the reactant side. On the product side, I'm going to have a Cl minus, I'm going to have 3 water molecules, and I'm going to have 3 iodine molecules. Now, there's lots of ways you could check these to see for sure that you've got them correct. You can count at balance to see if the chlorines, hydrogens, iodides, oxygens all balance. But a really quick and dirty trick you can do is just to see if your charge is balancing. Because if your charge balances before and after, you've probably done it right. So the total charge coming from the chlorate ion was 1 minus, from the hydrogens, plus 6 from the iodines, minus 6. So we're at a total of minus 1 on the reactant side. Checking the product side, minus 1 on the chlorine, 0 charge on the water and the iodine. So we're looking at the overall charge on the species here, 1 minus. Since the total charge before is equal to the total charge after, I know we have this equation balanced correctly. Okay, what do we do when we're balancing in base? Well, if we're balancing a base, there's a final step, because a basic solution has more hydroxides than hydrogens. So if there was any free hydrogens floating around, the hydroxides would just eat them up. So let's just see how that would look. I'm going to do a whole other example, because we have to start with the acid balancing rules anyway. So here's another very simplified reaction. It's completely unbalanced. We're going to balance it in base. But to do that, we start by balancing it in acid. And again, remember the steps. You do your redox species first, then your oxygens, then your hydrogens, and then your electrons to balance the charge. Finally, we'll do the base step. Okay, we're going to need to start by figuring out our oxidation numbers. Chlorine minus 1 has an oxidation number equal to the charge of 1 minus. The chlorate ion, we've got minus 2 on each of the 3 oxygens for a total of minus 6. That means we have to have a plus 5 on the chlorine to maintain this minus 1 charge that we have on the chlorate ion. And molecular chlorine has an oxidation number of 0. This is a split reaction. I can see that some of the chlorines went up to plus 5 and some of them went down to minus 1. And that's okay. We're still going to write the entire species, the whole thing that's circled on both halves of those lines, under the reduction and oxidation halves. So the reduction is where my charge went down. So we can see that some of my Cl2s turned into Cl minuses. There's my reduction half reaction. My oxidation half reaction is where my charge appeared to go up. So some of my Cl2s reacted to form chlorate ions, ClO3 minus 1 charges. Please be careful that you haven't dropped any charges because it's a really common error. All right, start by balancing the redox species. 2 chlorines before, a 2 means 2 chlorines after. 2 chlorines before on the oxidation half, 2 chlorines after. Okay. Redox species are balanced. Next, we're going to balance the oxygens using water molecules. Under the reduction half reaction, I don't see any oxygens to balance, so we're good. But under the oxidation half reaction, I have 2 groups of 3. I have 6 oxygens. So I need 6 oxygens on the reactant side, so I have to add 6 water molecules to get 6 of the oxygens in there. Step 2 is done. I've balanced the oxygens. Step 3, we now need to balance the hydrogens, and for this we use protons. There are no hydrogens to balance in my reduction half reaction, but I can see that I've got 6 groups of 2 is 12 hydrogens, so I need to put 12 protons here to make sure that this reaction will stay balanced. Don't forget the charges. It's really important to remember, otherwise we can't figure out the electrons. Okay, hydrogens are balanced. Finally, we need to figure out how many electrons each side needs. Again, I'm going to show you my thought process in green so it doesn't get mixed up with our equations. Molecular chlorine has no charge, so we're at a total charge of 0 before. There's 2 groups of minus 1, so we're at minus 2 after. We need to bring my charge of 0 down to minus 2, so we add 2 electrons to this side. So now my reduction half reaction is balanced. Taking a look at the oxidation half reaction, there is no charge coming from the chlorine. There is no charge coming from the waters. So there's no charge on the reaction, on the reactant side. On the product side, 2 groups of minus 1 is minus 2. 12 groups of plus 1 is plus 12. So at this side that we have, we are at a total of plus 10. Now, this is a much higher number than 0, so I could see that I am going to need to add 10 electrons to this side of the reaction in order for us to bring our charge down to 0 so it matches with the other side. Okay, let's get rid of all these little green numbers so that they aren't going to confuse the situation. All right, now before I add these 2 reactions back together again, what I need to do is make sure the electrons will cancel. So I already see my reduction half reaction is showing electrons coming in. My oxidation is showing electrons going out. They're on opposite sides of the arrow, so that's my first check. But clearly 2 and 10 are not the same number. Now I can make these both into 10 electrons by multiplying everything on the reduction side by 5 before I rewrite it. So we're going to do that, and we're going to write these again horizontally so that we can cancel everything out. So remembering to multiply everybody by 5. 5 groups of Cl2 is 5 Cl2s, and 5 times 2 is 10 electrons. Okay, that's the entire reactant side. On the product side, we've got 5 groups of 2 Cl minuses, so that's 10 Cl minuses. So there's my reduction half reaction, remembering to multiply everyone by 5. I didn't have to use a multiplier here. Sometimes you do. In this case, I did not. Writing everything out again. Again, I like to line up my arrows because you're less likely to make a mistake. On the reactant side, you've got diatomic chlorine, and you've got 6 water molecules. And on the product side of the reaction, you've got 2 chlorate ions, ClO3 minus 1s. You've got 12 protons, and you've got 10 electrons. All right, so this was a good starting point. We're now going to add these guys back together. We're still following acid balancing rules. The first thing you need to check is, do your electrons cancel? 10 electrons in cancels 10 electrons out. That's good. If they don't cancel completely, we know we've made a mistake. I'm checking to see if anything else cancels. Do I have anything else that's exactly the same on the before side and on the after side of the arrow? And I do not. I have chlorine, both equations, but they're both on the same side of the arrow. So what they're going to do is add up. 5 chlorines and this chlorine adds a total of 6 diatomic chlorines. We also have 6 water molecules. And on the product side, we're going to have 10 of the Cl minuses, 2 of the ClO3 minuses, and 12 protons. So now we're going to check to make sure that my total charges are the same. On the diatomic chlorine, we have a charge of 0. The water has a charge of 0. So we're at 0 charge before the reaction. On the after side, 10 minus 1s is minus 10. 2 minus 1s is minus 2. And 12 sets of plus 1 is plus 12. And this adds up to 0 charge after. This is balanced correctly, but it's balanced in acid. And I told you guys that when we want to balance anything in base, we just have to do one more step. So we're just going to do that now. I'm going to get rid of my green again, and we're going to do just that one more step. All right, so when we're balancing in a base, we know that there's going to be extra hydroxides, and the hydroxides are going to search out the protons. So I have 12 hydrogens, 12 protons there. So I could imagine that 12 hydroxide ions, which are OH minus 1, that's the definition of a base right there, are going to go and attract those 12 hydroxide ions. And when they get together, they are going to form 12 water molecules. We know that a hydrogen attaches itself to a hydroxide to make water. HOH is water. So for each one, we're adding up to make a total of 12. But to keep my reaction balanced, if I add 12 to this side, I have to add 12 hydroxides to the reactant side as well, because what you do to the left, you have to do to the right. Okay, let's take a look at where that leaves us. If I write out again what I have at this point, I've got 6 Cl2s and 6 water molecules and 12 hydroxide molecules on the reactant side. On the product side, I've got 10 Cl minuses and 2 ClO3 minuses and 12 water molecules. Well, already I can see that I've got water molecules on both sides. I've got 6 of them here and 12 of them there. So we can cancel yet some more. All 6 of these will cancel. 6 of the 12 will cancel, and I'll have 6 left over. So my final net equation that I will have will be 6 chlorines, and this water is gone, 12 hydroxides, react to make 10 Cl minuses, 2 ClO3 minuses, and 6 water molecules. Again, we can check this by checking our charges. 6 groups of 0 is 0. 12 groups of -1 is -12. So I have a total of -12 on the reactant side. 10 groups of -1 is -10. 2 groups of -1, -2. 6 groups of 0 is 0. So I have a total of -12 on this side. They are equal. This reaction is balanced properly in base. Okay, now we could try one more, and I'm going to get you guys to try this one on your own. Pause the video and see how far you can get. When you get to the point that you get stuck, start the video up again, and we'll follow it along together. We're going to balance this reaction in acid. This time we can tell it's an acid reaction because I can see that there's protons right in the reaction. So these guys are going to drop out when we first separate our redox species, but they'll pop back in the final net equation. So get your little redox chart available and pause the video here. And let's see if we can get as far as assigning your oxidation numbers and writing your half reactions as a starting point. Okay, pause the video now. All right, let's look at that first step together. We start by assigning all of our oxidation numbers. We're going to see who went up and who went down. Manganese went from an oxidation number of +4 down to an oxidation number of +2. So that's my reduction. So I'm going to write the word redox, and I'm going to write my reduction half reaction under the word reduction. So for my reduction half reaction, we had MnO2, manganese dioxide, turns into Mn plus 2, there's the manganese ion. All right, where does my charge go up? Well, it goes up on the nitrogen. It went from +3 in the nitrate ion up to +5 in the nitrate ion. So we will write that entire reaction under the oxidation side because the oxidation number went up. So we have NO2 minus turning into NO3 minus. Always a really good point at this point to check to make sure you've copied down all of your charges correctly. All right, now you need to do your balancing steps. Remember the sequence. You start with your redox species, then do oxygens, hydrogens, electrons. If you've gotten this far and you got stuck, pause the video again, pause it here, and we will see how this goes. All right, let's see how far you managed to get. I had 1 manganese before and 1 manganese after, so my redox species was balanced. To balance the oxygens, there was 2 on the reactant side and none on the product side, so I add 2 water molecules to give me 2 oxygens. I know I have to put on 4 hydrogens, so I'm going to add 4 protons to give me a total of 4 hydrogens. Finally, I'll balance for charge. And again, doing my thinking in another color so it doesn't get mixed up with my reaction. I've got 0 charge from the manganese dioxide, +4 from the hydrogens, gives me a total of +4 on the reactant side. I've got +2 from the manganese, 0 from the water, gives me a total of +2 on the product side. Electrons always go to the higher of the 2 charges because they bring charge down. And so I'm going to need 2 electrons to bring the charges to the point where they're equal on both sides. We'll now do the same thing for the oxidation half reaction. 1 nitrogen before, 1 nitrogen after. Our redox species are balanced. We have 2 oxygens on the reactant side and 3 on the product side. So the reactant side needs 1 more. We'll add 1 water molecule to add 1 more oxygen. Then I've got 2 hydrogens that need balancing, so we add 2 protons, remembering my charges. All right, let's check the overall charge so we can see how many electrons to answer. From the NO2 that I tried ion, I've got 1 minus a charge, and from the water, 0. From the NO3 ion, I've got 1 minus a charge, and from the 2 protons, plus 2. I've got a total of 1 minus charge before, positive 2 and minus 1. I've got a charge of plus 1 after. Electrons always go to the higher side, and so these are going to go on the product side. And to bring plus 1 down to minus 1, I need to add 2 electrons. Now I've got a total charge of plus 1 before and plus 1 after. Okay, we now need to see if my electrons will be available to cancel. I've got electrons on the reactant side here, on the product side there, so they will. And in this case, we actually find that we have the exact same amount of electrons before and after. So we can go ahead and start writing out this equation and canceling all of our charges and our common ions and see what we have for an overall equation. It was nice this time that we didn't need to use a multiplier for the electrons to cancel. But I've written both the reduction and the oxidation half reactions horizontally so that we can more readily cancel the remaining ions. First, check to make sure your electrons cancel. 2 electrons in cancels 2 electrons out. Quite often there are other things that need to cancel, and indeed this time there are. I have protons on both sides of the equation. I have 2 protons here that can cancel 2 of the 4, and there will be 2 remaining protons left over. I also have water on both sides of the equation. This water molecule will cancel 1 of the 2, and we'll have 1 water molecule as a product left over. My overall net equation is now MnO2, and I've got 2 protons remaining, and I've got an NO2 minus, and then as we have for products, we've got Mn plus 2, and I've got 1 water molecule remaining, and I've got NO3 minus. Again, a quick check to make sure my charge is balanced is a fast way to tell if we've done this correctly. The manganese dioxide has no charge, so we'll give it a charge of 0. 2 plus 1s is plus 2, and a group of minus 1s is minus 1. So we are at an overall charge of plus 1 on this side of the equation. From the manganese ions, there's 1 group of plus 2, so we got plus 2 there, 1 group of 0, and 1 group of minus 1. Again, we're at a charge of plus 1 there. My charges are equal. My reaction is balanced. So we've done now several examples for you of balancing reactions in acid and in base. I've got lots of practice for you. In your notes, you have this set of equations that we have for balancing in acid and in base. That's a great place to start. You also have a whole bunch more questions available for you in your textbook on balancing in acid and in base. And also I will link some other videos showing you even more examples below this video in the comments.